Calculus 2, section 7.4, I didn't write that down. Inverse trig functions. First of all, what are the inverse trig functions? Well, if you remember, the sine function has a graph that we usually think of just this part, but it does go on forever and ever and ever and ever. So its domain was all the real numbers, negative infinity to infinity, and its range was from a negative 1 to 1. But we need an inverse function. And so we can't have this many to 1 function. It won't have an inverse. We've got to make this a 1 to 1 function. So we're going to take and chop off everything to the right and everything to the left where this turns around, so to speak. So this will go up to pi over 2 and back to a negative pi over 2. It'll still give you the negative 1 to 1. So that 1 to 1 function is what you need. We are now going to talk about from negative pi over 2 included to positive pi over 2. That's for the restricted sine function. For the inverse sine function, which we use this negative 1 exponent, also called the arc sine, we're going to flip the x and the y, and we really flip it along this y equals x line. So this will now be, instead of negative pi over 2 to pi over 2 on the x, it's going to be negative pi over 2 to pi over 2 on the y, and a negative 1 to 1 on the x. So it's still these points. Negative 1, negative pi over 2 is going to be, I should say negative pi over 2, negative 1 will be negative 1, negative pi over 2. 0 and 0 is still, and pi over 2 and, 1 and pi over 2. But which way is this going to go? Well, because it looked like an S before, it's going to sort of go like this for the graph. But start and end here. For the inverse sine function, it's an inverse function. So now we flip the domains and ranges. The domain is going to be from a negative 1 to 1, and the range will go from a negative pi over 2 to pi over 2. And we're going to do that for all 6 trig functions. So the inverse cosine, well, let's do the inverse tangent first. If you recall, the tangent, one of its pieces, went from a negative pi over 2 to pi over 2. And so because we can just cut off all the rest of the pieces, that's what we can do. This can also be written as arctan. Now, instead of having a vertical asymptote at pi over 2 and negative pi over 2, we're going to have horizontal asymptotes at negative pi over 2 and pi over 2. This went lower left to upper right. Now it's going to go, if you can envision this, we're going to go from the center and approach as we go negative, the negative pi over 2 asymptote and the positive pi over 2 asymptote. The inverse secant, also called the arc secant. Now this one takes me, the domain of this has switched also. Used to be the domain being negative pi over 2 to pi over 2. Now the domain is all the reals from a negative infinity to infinity, and the range is that negative pi over 2 to pi over 2, but you leave the endpoints off because those are the asymptotes. The secant, well, secant comes from cosine, right? And the cosine is going to have something like this. And we're going to use then the top part of this because we've got this vertical asymptote. This is how we're going to restrict it. It's going to go from 0 to pi. And here's the 1 and negative 1, but we're going to go beyond that. So we have, when we flip this over, at pi over 2 is our asymptote horizontal. And here is 0 to pi on the now vertical axis. And the negative 1 and 1. And we're going to start at the 1 and approach the asymptote. And start at the negative 1 up here at pi and approach the asymptote. So the domain is going to go from a negative infinity up to negative 1 inclusive union, then a positive 1 up to infinity. The range is going to give me this 0 to pi. But we have to leave out the center of that at pi over 2. So we're really going to go from, include 0, go up to pi, skip over it, and then go up to, 0 to pi over 2, skip over the pi over 2 and go up to pi, but include that. Now, we can do the others also, but maybe I'll leave that as far as you to get. The way I try to remember these easiest is with circles. For the three trig functions that are predominantly, I guess, sine functions, that is the sine and the tangent because sine is in the numerator, and the cosecant because it's 1 over sine. For the cosine trio, it would be the cotangent because cosine is the numerator, and the secant. Now, what these sines use is really this right side, and the cosine uses the top. But this, because this goes from a negative pi over 2 to pi over 2, and from a negative 1 to 1. This goes from 0 to pi. And that's what helps me remember this. The sine includes all this stuff. The tangent leaves out the end points. And the cosecant leaves out this middle point. The cosine takes all of this with 0 and pi. The cotangent leaves out the end points, 0 and pi. The secant leaves off this middle point at pi over 2. So remember, these are for the restricted domains. This is not. You can use this for the inverse if you think about switching the x and the y, because that's all you need to do. So if you look at the way we find these derivatives, because remember the inverse, the arc sine, is really the inverse of this trig function. We can use our derivative of the inverse idea. Remember, the derivative with respect to x of the inverse of some function at x is equal to 1 over the derivative with respect to x of the function at f inverse of x. So remember, we got to put that value in. So we want to find the derivative with respect to x of the inverse of the sine. We want 1 over the derivative with respect to x of the function, the sine, inverse, I'm sorry, the sine, not the inverse. Let me get rid of that. But we want that at the sine inverse of x, if that makes sense. So, let's continue this way over here. So this is now 1 over, what is the derivative of the sine? Well, it's the cosine. At the inverse of the sine of x. And because we're just using x, we don't need to worry about the chain rule. But to hold it, what is the inverse of the sine of x? Well, we'd like to get this in terms of sine if possible. So I know that the cosine of some angle is 1 minus sine squared of that same angle, sine inverse of x, if I take the square root, right? Does that make sense? Because this is a trig identity. It's the cosine squared plus sine squared equals 1. So take the cosine, you subtract, it's 1 minus sine squared, take the square root. And you can get 1 over the square root of 1 minus, now what is, think of this as the sine of the inverse sine of x. What is this going to do? Well, in this case, the sines are going to cancel, and then we square it. So if you take the inverse of the sine and send it over to the range of that inverse, then you take that and bring it back essentially with this sine here. You just get back to where you started, x, and then square it. That is what we get if we just use x. Remember, if we've got the chain rule and we've got the inverse sine of u, we have 1 over square root of 1 minus u squared du dx. That's the one to remember. Remember to take that derivative using the chain rule. So far, so good. That's the first one we'll memorize. Now, well, usually we go sine and then cosine and then tangent. But we're going to do these inverse cosines because we're going to take care of all the functions, sine, tangent, secant first, and then take care of their cofunctions because it makes it a little easier. So, the question is, the derivative with respect to x of the inverse tangent of x. Well, once again, it'll be 1 over, and I may skip a little bit here. What's the derivative of a tangent? It's the secant squared of the inverse of tangent of x. Well, hold it. That's negative 1 inverse. Okay. What do we know about secant squared? You remember the identity that says 1 plus tangent squared theta equals secant squared theta? That's what you were probably thinking. So this is really 1 over 1, secant squared, let me try this again. It's 1 plus tangent squared. But it's of the inverse tangent of x, which is sort of nice because, once again, when we take the inverse, we have that restricted domain that we've been using, and therefore we know exactly where it's going to go. We don't have to worry about being way down 30 pi over or 2 type of thing. Because we know it's in between the negative pi over 2 and pi over 2. So this inverse tangent takes x and sends it over, and then the tangent brings it back, and you wind up at x again. So it's really 1 plus x squared, or if we want the derivative with respect to x of the inverse tangent of u, then we have 1 over 1 plus u squared, and then chain rule, du dx. So that's our next one. We'll take care of the cotangent later, just like the cosine later. Next will be our friend the secant. So the derivative with respect to x of the inverse secant of x. Now what you're probably saying is, well, aren't we going to use that 1 over? Well, it was nice with the sine because the derivative of sine was cosine. It was nice with the tangent because the derivative of tangent was secant squared. We didn't get 2 trig functions like we do with the secant. The derivative of the secant is secant tangent, and it's sort of hard to get rid of all that stuff. So, how do you take care of this? Well, first of all, if y is equal to secant inverse of x, then what is, if we rewrite this, we can say that the secant of y is equal to x, right? And then, if we take the derivative with respect to x of both sides, on the right side we get 1. On the left side we get the derivative of secant is secant y tangent y dy dx. So dy dx is equal to, well, it's 1 divided by the secant of y, the tangent of y. And we found out what dy dx is then. If y is inverse secant, right? That's what we want, the derivative of this inverse secant. But hold it, let's make it nicer. We'd like to make this look similar to the other forms. If we know that, as we saw before, 1 plus tangent squared theta equals secant squared theta, then we also know that the tangent squared theta equals secant squared theta minus 1, and the square root of the tangent of theta equals plus or minus the square root of secant squared theta minus 1. So we're going to take that and put that in here, this secant y, so this is 1 over, the secant y we're going to replace with our x here. The tangent of y we're going to replace with this square root. So it's going to be secant squared y minus 1, or in this case. But just a second. So the tangent of y is the secant squared y minus 1. And if I can squeeze it in here, this is 1 over x times, well, secant of y, remember, is x. So secant squared is really x squared minus 1. Now, we need to worry about positive and negative. But if you remember our graph, the graph had this at 1, and this at pi over 2, and this was approaching here. And then it had at -1, and this was pi, and this was approaching here. Notice all of our values for the range are positive, except for maybe 0, but that's okay. So we need to make sure that this is always positive, so they're going to put in absolute value. And if we use the chain rule of the inverse secant of u, we get 1 over absolute value of u times the square root of u squared minus 1 times du dx. That's the one to remember. So how do you keep these straight? Let's see. For the sine, it was 1 over the square root of 1 minus x squared. For the tangent, it's 1 over, no square roots, 1 plus x squared. For the secant, it's 1 over what's got a square root, but instead of 1 minus, it's minus 1, so it's x squared minus 1, and then you need the absolute value of that square root on the outside. I guess that's what I use to try to remember these things. So, let me change colors here, because this is going to be a sort of a new way of looking at this. I guess our book looked at this that way, so it's not completely new. What is the cosine inverse of x plus the sine inverse of x? Well, let's see here. Let's look at a right triangle. We'll call this A, and this B, and this C. And this is because of cofunctions, right? We know that when we take angle A, the measure, and add the measure of angle B, we get 90 degrees, or pi over 2. Remember, these inverse trig functions are really just angles. So if I say the cosine of A is the adjacent over the hypotenuse, and if I call this x, I guess, and this 1, the cosine of A is x over 1. The inverse cosine of x, let me write this down, cosine of A is x over 1. If I find the inverse, take the inverse of both sides, then I get A is the inverse cosine of x over 1, which is really just the inverse cosine of x. So that's this angle A. And if I take the sine of A, the sine of B, it's the opposite, x over 1. But B is the inverse sine of x over 1. So the inverse cosine plus the inverse sine of x is just A plus B, which is just pi over 2. So now that we've got that, we can solve this for cosine inverse of x, which is pi over 2 minus the sine inverse of x. Well, hold it. When we take the derivative of that left side, we take the derivative with respect to x of pi over 2 minus the derivative with respect to x of the sine inverse of x. Well, hold it. The derivative of a constant is 0. And the derivative of sine inverse, was that 1 over the square root of 1 plus x squared. I'm sorry, 1 minus x squared. I'm thinking of the tangent again. But hold it. This is just -1, or take the opposite of the sine inverse. So the only difference between the sine inverse derivative and the cosine inverse's derivative is one's positive and one's negative. Suppose it's going to work for the others? You betcha. So let me see if we can write these on one page, if it'll fit. The derivative with respect to x of the sine inverse of u is 1 over the square root of 1 minus u squared du dx. The derivative with respect to x of the inverse cosine of u is a -1 over the square root of 1 minus u squared, du dx. That's a u up here. The derivative with respect to x of the inverse tangent of u is 1 over 1 plus u squared du dx. And I guess I'm keeping this order. I don't know. It doesn't really make any difference. The derivative with respect to x of the cotangent inverse of u is a -1 over 1 plus u squared du dx. And the derivative with respect to x of the secant inverse of u is 1 over the absolute value of u times the square root. It's not 1 minus u squared, it's u squared minus 1 du dx. And the derivative with respect to x of the inverse cosecant is a -1 over absolute value of u times the square root of u squared minus 1 du dx. So these are not so bad to memorize, perhaps. Let's go through some examples where you can learn how to figure these out. This first one shouldn't take too much room. I'm going to change colors just so it doesn't. Okay, this is on page 404, that assignment section, and this is number 6. We're supposed to find the derivative. No, not for this. This has a part A, part B, and part C. We're just going to part A. We're supposed to solve for theta. If we know the cosecant inverse, square root 2 is equal to our theta, what is theta? Well, let's see. The way I usually solve these is I know if I've got the inverse, I can move that to the other side, leave the square root of 2, and I get the cosine of theta. Not the cosine, cosecant. That's right. Cosecant of theta. Well, let's see. The cosecant is just, let's see, square root of 2 over 1 is 1 over the sine of theta. Well, hold it. That means that the sine of theta, I'm going to switch sides, is equal to 1 over the square root, or square root of 2 over 2. And that means that this has got to be a 45-degree angle, pi over 4. Is it positive or negative? Well, it's easy to see because this is positive, it'll stay positive. So theta is equal to a positive pi over 4, and that can be my answer. Put it in the answer box. I don't know how you want to get some of these. On the next page, let me show you one way to memorize this, if we know that the tangent of theta is equal to the sine of theta over the cosine of theta, and that the sine of theta is the square root of 0, 1, 2, 3, 4 over 2, and the cosine of theta is the square root of 4, 3, 2, 1, 0 over 2. And we can say this is 4, I'm going to use radians. For 0 radians, pi over 6 radians, 30 degrees, pi over 4 radians, 45 degrees, pi over 3 radians, 60 degrees, pi over 2 radians, 90 degrees. Then, when we had the sine is equal to the square root of 2 over 2, we can say that's the pi over 4. This is easy to reproduce, and all these special angles are included. You have to just get it down if you want to find what the sine is of pi over 4, square root of 2 over 2. The sine of pi over 2, it's the square root of 4 over 2, which is square root of 4, of course, is 2. 2 over 2 is 1. So you might want to reduce it. How about the same page, number 10? The secant of the cosine inverse of 1/2. This is going to equal, well, let's see. The cosine inverse of 1/2, that's some angle. I'm going to call it theta, is the cosine inverse of 1/2. All these inverse trig functions, I think of angles. So using theta helps me remember that it's special. So the cosine of some angle is 1/2. If you look at this, cosine is 1/2. That angle must be pi over 3. And what's nice about the restricted domains, I don't even have to worry about going around the circle 100 times, just that 1/2 time. So this is really, this says that theta is equal to pi over 3. So the secant of pi over 3 is what I'm looking for. But the secant is 1 over the cosine of pi over 3. And the cosine of pi over 3 is 1/2. So the secant 1 over 1/2 or 2. Does that make sense? So write this down if you don't have it written down, and keep that around. That could be one of the first things you do on a test. I remember doing that on Trig. Write that down first. Then I just refer to it whenever I need it. So here's number 18, a limit. Being able to visualize these limits with the graph, I think is so helpful. So, if you don't have it down yet, you need to figure out how to draw the graph of these inverse trig functions. Let me show you what I do. I start, because the secant is even hard for me, I start with the cosine, and here's pi over 2, and here's pi. And I know that I only need, here's -1 and here's 1. I only need half of it, from 0 to pi. So this is my restricted cosine. The secant for this particular picture is all the rest of the stuff. It has a vertical asymptote where the cosine is 0. And at these points, these peaks and valleys, I'm going to approach the asymptote. But now, this x has got to become the y-axis, and the y has got to become the x. So you flip it through this y equals x line, and you can either do that physically or just say, okay, now I know that I've got, instead of everything to the right of the y-axis, I have everything above the x-axis. This goes from 0 to pi, so on my y it's 0 to pi. Halfway between is my asymptote, now horizontal instead of vertical. There's a 1, there's a negative 1, and I know that if this is 0, 1, then at 1, 0, I have a point, and I approach the asymptote. At pi negative 1, so I say negative 1 pi, I have a point, and approaches the asymptote. Okay. And maybe you can do this all in your head, and I'm just not as smart as you, but that's okay, because this at least gives me 4 steps. So as x goes to negative infinity, screaming off in that direction, this function goes to pi over 2. And I've got my 4 steps, because I'll count these as a couple. Does that make sense? I hope it makes sense. Now the next problem needs more than just this part of the page. So number 22. Maybe I'll change colors here. A nice hot pink. Or maybe this is chartreuse. I don't know. Number 22. We're supposed to find the derivative. Okay, we're given y equals inverse cosine of 1 over x. Okay, this is where you use the chain rule. Remember the derivative with respect to x, and this can help you if you need to memorize these. It is negative 1 over the sine stuff. Let's see, it's the square root of 1 minus u squared du dx. Okay, so the derivative of y with respect to x is a negative 1 over the square root of 1 minus, well, this is the u, 1 over x, so it's 1 squared over x squared. And then the derivative of 1 over x. Well, you might even do that here. That's the derivative of x to the negative 1, which is you subtract 1, right? So it's x to the negative 2, and first multiply by the exponent and then subtract 1. So this is a negative x to the negative 2, which is a negative 1 over x squared. So that's what we can put out here. Let's see, our textbook, I think, has written this a different way. So, what I'm probably going to do for the test is not make you go through a bunch more work. This is where you can stop. If I say do not simplify, then stop. Go on to the next problem. Matching the textbook is a little harder because they don't write it this way. The textbook writes it as 1 over the absolute value of x times the square root of x squared minus 1. So that's, if you want to match that, you're going to have to do a little work. First of all, this negative 1 and negative 1, that gives you the positive 1, so you've taken care of that. This square root, I'm going to write 1 as x squared over x squared minus 1 over x squared, so you get x squared minus 1 over that common denominator x squared times x squared out here. Okay, so If you rewrite this, you can rewrite that as 1 over and this is the square root of x squared minus 1 over x. This is times the x squared, of course. Now this becomes, because you've got this reciprocal 1 over, so we can have this as x over, I'm going to put the x squared here, times the square root of x squared minus 1. And then you can say, well, hold it. This, how do you want to say this? If I divide this, I'm just going to get an x, right? So I'm going to get a 1 over x square root of x squared minus 1. But this x squared is always positive. In fact, if we take the derivative of all this stuff, I wish I still had that cosine, the graph of the inverse cosine. Remember the cosine looks something like this. So the inverse cosine, if you have this at positive 1, it does something like this. The point being, I guess, this is always negative. But this is not just the inverse cosine of x. This is the inverse cosine of 1 over x. So all of this negative really becomes the inverse. So it's all the rest of this. And it's all the rest of this. If you think about it, the inverse cosine of 1 over x is the same as the cosine of y equals 1 over x. So 1 over the cosine of y equals x, and 1 over cosine is secant. So all of these slopes are positive. So I need to make sure this is positive and put an absolute value. You could have gone up here and said, hold it, inverse cosine 1 over x, that's the same as inverse secant. I'm sorry. It's the same as secant x. Inverse secant, excuse me. And that would give you this right away. Anyway, sort of interesting. When you do these problems, I know you guys have all this extra free time, so it's interesting to look at. But do bring in some other stuff and say to yourself, does that even make sense? When you graph this inverse cosine of 1 over x, you do get something that looks like the secant, inverse secant, which always has a positive slope. So this, what you put in here is the inverse cosine of 1 over x. I had to make the window a little bit nicer, but it's sort of neat that you can do that and help yourself out. Take a look at that. Convince yourself, why does this have to be absolute value? Because it's always a positive slope. When you find the derivative, you're talking about slope. Okay. So this is number 32, and we're given y equals the inverse cotangent of the square root of t minus 1. So they want to find dy dt. I want to bring in my calculator again because this can be helpful. You can't rely on having this all the time, and yet, if you've got access to it and you're a little bit confused, a graph can help. Now, what's important here is that this, how do you want to say this? The inverse cotangent is a little harder to get than the inverse cosine or the inverse tangent. It is not 1 over the inverse tangent. And I hope you understand why. We're going to go underneath the calculator for this. So, let's just call this theta for now. if y is equal to the inverse cotangent of theta, then the cotangent of y is equal to theta, some angle. Now, the cotangent is 1 over the tangent of y, which is still equal to theta, but you can think of it as theta over 1, because then you can say that the tangent of y is equal to 1 over theta. And then you take the inverse, you can say y is equal to the inverse tangent of 1 over theta. So it's important to recognize, if y is the inverse cotangent of an angle, it is not 1 over the inverse tangent, it's the inverse tangent of 1 over. You're taking the reciprocal of the wrong place. So this is really the inverse tangent of 1 over the square root of t minus 1. Does that make sense? Now, I'm only doing that so I can graph it, because you don't need that to find the derivative. But let me bring my calculator back up, because sometimes it's good to know this is always positive, sometimes it's negative, things like that. But I need the inverse tangent of 1 divided by the square root, in parentheses, we've got to use x, minus 1, close the square root, close the tangent, inverse tangent. Let's zoom Trig just to see what it gives us. So the inverse tangent is just this. If we know where this is defined, it's from a negative pi over 2 to pi over 2, right? You might be saying, well, hold it, the inverse cotangent doesn't look like that. It keeps on going to the left here. Well, remember, our argument, 1 over the square root of t minus 1, is going to restrict some stuff because of that square root. You can't see square roots of negatives. So it's going to stop here at 1. I think I put these at pi over 2. Let me look. The window for the x, yeah. The scale for the x-axis should be 1s. And now when we graph it, we'll see that at 1 is where this thing starts, because anything to the left of 1 will give me a negative number. And I can't even equal 1 here because that's in the denominator. So this graph is good, and what it shows you is you have always a negative slope. So this is going to always be negative. Okay. So I'm going to still start from up here. And dy dt, remember it's a negative 1 over the absolute value of the square root of t minus 1 times the square root second. And this is why I should write these down, I guess, here. This is not right. I was doing a cosecant, not a cotangent. So remember, it's just a negative 1 over 1 plus u squared du dx. Okay, let me go back up here and get this. So it's 1 plus the square root of t minus 1 squared, and then the derivative of this. Well, we're going to think of this as t minus 1 to the 1/2. So we're going to take 1/2 times this t minus 1 to the negative 1/2, so it's going to be over the square root of t minus 1, t minus 1, times the derivative of t, which is just 1. Does that make sense? So it's 1/2 t minus 1 to the negative 1/2, which is square root underneath, times 1. Okay, this is negative 1 over, we're going to multiply this by 2, so I'm going to get a 2 square root of t minus 1, that's times the 1 there, plus a 2 times the t minus 1, I'm sorry, this is squared, golly. This is t minus 1 times 2 times that. So it's really 2 times t minus 1, and we have a 1 plus a 1/2 or 3/2. Okay. So I'm going to factor, this is really square root of t minus 1 cubed, right? So I'm going to factor out the square root of t minus 1. So negative 1 over, and a 2 also. 2 square root of t minus 1. And I'm going to have left a 1 plus, this is going to be just a t minus 1 squared. Square root of t minus 1 squared. So it's just going to be a t minus 1, which gives me a negative 1 over 2, and this 1 cancel, 2, and then the t, times the square root of t minus 1. Wow, I made that so complicated. But it does become a little confusing. I did get 4 steps. So that's good. So let me get rid of some of this because it was confusing. And I think there's a better way to explain it. So let me give me a minute here. I guess I should have just started over. Maybe. But what I've got written here is still good. Once again, it looks like the inverse tangent. But the inverse tangent, with that 1 plus u squared, how do we make it look exactly like that? Well, if we want, we can take this, the 4 plus 3t squared, if we want to make that become 1 plus u squared. We can factor out a 4, and this will then be 1 plus 3/4 t squared equals 1 plus u squared. This then means that we've got 1 plus 3/4 t squared equals 1/4 1 plus u squared. Okay. Then u squared is equal to 3/4 t squared. And this is also being a little confusing because that 1/4, I guess when you put it up here, you should say, okay, first of all, I'm going to take out a 1/4. Don't worry about the limits yet. And this will be 1 plus 3/4 t squared. Then I'm going to say that u is equal to, take the square root of both sides, square root of 3 over 2 t. But I don't have, I'm sorry, that's what u is, so du is the square root of 3 over 2 dt. Okay. Well, the dt is here, but I don't have this square root of 3 over 2, so I need a 2 over the square root of 3 with my du. So I've got a 2 over the square root of 3 and a 1/4, and the du is now going to replace the dt, and the 1 plus 3/4 squared is going to, because I pulled out this 1/4 here, is going to be 1 plus u squared. Does that make sense? This 1/4 can be confusing. It's not 1/4 in the denominator. I guess you'd have to do it differently if you did it that way. I'm just pulling out the 1/4 and making this a 1 plus, so I can use a u squared as 3/4 t squared. Does that make sense? So these are really not equal, I guess. I'm trying to get the same pattern. Now, also, if t is equal to a -2, then u with a -2 here is a negative square root of 3. So this is a negative square root of 3. And at t equals 2, then u is equal to positive square root of 3. If we take this 2 goes once, goes twice, we have 1 over 2 square roots of 3. The derivative of du over 1 plus u squared is inverse tangent of u, evaluated from a negative square root of 3 over square root of 2 with the square root of 3. Now, what you need to remember is the tangent is sine over cosine. The tangent of pi over 3 is square root of 3 over 2 over 1/2 because it's sine over cosine. So this u is a pi over 3. So when I put in the square root of 3, the angle that goes along with that with tangent is pi over 3. I'm running out of room here. So I have 1 over 2 square roots of 3. And this first one, when I plug in the square root of 3, I get a pi over 3. Minus, when I plug in a negative square root of 3, I get a pi over 3, but it's negative because I need that in the fourth quadrant. This then is a positive 2 pi over 3s. Times this, the 2's cancel. And we get pi over 3 square root of 3. If that makes sense. We have 2 pi over 3s times this, the 2's cancel, and it's pi over 3 square root of 3. Was this confusing? What you want to do with this particular denominator is make it look like 1 plus u squared, and making that 1 is probably the easiest thing. You can't subtract 3, you've got to divide by something that'll make that a 1, and so it's the same thing. Factor that out front so that you can take care of that later. And then your u squared is what's left out here. Okay. Well, send me some of your questions so I can practice some more of this. I get a little better as I go. I just need more practice.